So today I would like to, when we talk about aquaculture, of course it is a mixed kind of, the saline water becomes important, and so I would like to take a little bit the other part of, because antibiotic has been covered very nicely by David, so I would like to tell about seawater intrusion and these things. And my presentations will have this, the segments. So coming to the seawater, every time perhaps the very common is seawater intrusion. And if we will see that this is the one thing that everybody understands, that any the interface is getting very, very much important nowadays, is that whether it is land and ocean interface or even the atmosphere and water interface. So this is, we are talking about interface. So there is a balance between seawater, margin and freshwater system. And so then if there is a upwelling, if there is a withdrawal, then again, something which was here will be in this, and there is a rule, there is by this professor said that says that if you will withdraw 1 foot or 1 meter of the fresh water, the salt water will intrude or upwelling will happen 40 times of that. So this is very much important, that even if we take a water out from a aquifer which has an interface with the saline water, so then this is really very much important. So then what will happen is that if we will withdraw the water, then this interface will change and the seawater will intrude to the fresh water. So this is, all of us, or most of us know that the seawater intrusion and like that. But the other side of the coin is submarine groundwater discharge. It is not only that only the seawater intrude to the aquifer, but even if there is no anthropogenic interface, then still there will be lot of there will be the sea, due to just hydraulic, so there will be a lot of the fresh water is likely to go into the seawater, and that is called submarine groundwater discharge. So seawater intrusion, we can say that the submarine groundwater discharge is just opposite of the seawater intrusion. Then, so coming to that okay, so we have already talked. I hope that I am able to, yeah. So this is, so what is happening is that so far I have talked is that there is a balance between seawater and freshwater. And if we withdraw, then the seawater will intrude. And if you will not withdraw, then still there will be recharge of the groundwater and it will go to the seawater. Now, that is the one kind of seawater, the submarine groundwater discharge. But another kind of is that because of the wave setup, you know that there is a high tide and low tide. So when there is a high tide, so the saline water pushes the groundwater. And when there is a low tide, then the groundwater will push down to the saline water. And in that process also, there will be a lot of groundwater will be discharged into the sea. Now, what is the point? I mean, why it is critical? One thing is that this is a interface we are talking about, and groundwater has no dissolved oxygen. Very less, because it is very underground. Then it has very high nitrate or the iron. Even we know that arsenic, chloride and those things are there. So it will come to the seawater. And eventually it is also going to affect our, and if there is it is reported that wherever the groundwater discharge is more, the community is changed, the fish or the microbial community and like that. So this is the one we are trying to understand in Indian coastal city, the coastal zone. And then there is so this thing I have already talked about, that recirculation and like that. So I am going to tell you is that the methodology that we have adopted is reviewing archival data we have taken from the different organizations. Then we have applied some remote sensing, and also we have done some survey. and then we have also did some gradient or the push point sampler. So the push point, so I will come through one by one. But I would like to tell you is this one is that why it is important to quantify the fresh water that can be tracked sustainably. So there is the two things. Not only that if submarine groundwater discharged into the seawater, then what is the fresh water availability? People say water everywhere, not a single drop to drink. Is that if we can store or use that water throughout the year. So if we know that how much fresh water we are losing to the sea, we can develop something so that we can use those fresh water. So this quantification will help that way also. But here I will talk about a little bit more from the aquaculture perspective also. So then let me introduce India, the more specifically. So in that case, we are the peninsula country, and here we have around 6,000 kilometers of coastal line. So still it is, we are not island country, but still we have a lot of coastal line. Though we don't have the nice fish food that is cooked here. So in that case, I am talking about, I'm sorry, this is some problem. So here, this is and we have this, the west coast and east coast. So then east coast is here, Bay of Bengal and like that. And so these are the studies published this year based on this review, is that how many studies has been done on seawater intrusion and submarine groundwater discharge. In Chennai, which is one of the 4 major cities in India, we have even until it is reported 16 kilometers of the seawater intrusion has happened only in the city. So in that case, my study is confined to this place that is called Glujarat. So I am talking about 1600 kilometers of the coastal line of the west coast. So this is Gujarat. And probably I come from the near there, Mumbai. So this is the place we have done. So we have collected a lot of data from all that how groundwater fluctuation has happened over the time, and this is electrical conductivity. And you can see that the more, and then also we have plotted the pre-monsoon and post-monsoon slide, the water fluctuation to understand that how much recharge happens. And we have seen that there is a lot of in the south. Okay. Can I use So this is cursor. So in South Gujarat there is a more recharge happens, and in the north part we have a little bit less, and we have a bit more the saltwater intrusion. What we have done is that from using remote sensing, we have collected the seawater surface temperature. And seawater surface temperature, this is the several years. You can see that 2011, 12, 14, 15, 18, 19. And every year on the August monthly average we are plotting here. You can see that and based on the temperature difference, we identified 3 points, P1, P2, P3. And to understand that maybe P1 and P2 are the place where SGD is occurring because the temperature difference you can see then the rest of the sea surface. And P3 also has the temperature difference, but perhaps probably it is a reverse of submarine groundwater discharge. So this is the first, we have seen the groundwater fluctuation, then we are doing the surface water temperature. And then we went to the field, actual field, and it took us around 1 month of work to take the sample every 5 kilometers along the 1600 kilometer coastal line. Then we have analyzed the many parameters in the field, and then we are analyzing a lot of parameters after coming back, which includes the heavy metals, antibiotics, and the other things. And but here I am going to present some preliminary tests because still the analysis has not been completed. So here you can see that I have plotted from south Gujarat to the north Gujarat. So from the starting down to the going up, And we have put the sample, this circle is the seawater, and the other, this empty circle are the groundwater. So you can see the several times, like, okay, if there is a DO difference, so if DO is decreasing in the sea portion, so it means this is the area where maybe the groundwater discharge is happening. Same thing is, which is also evident in ORP, and this is, so then P1, P2, those locations we have shown here. So in that case, because there is a clear difference between the TDS, or the salinity, because we know that the seawater salinity will be much higher and then the groundwater will be less. So sometimes where there is a groundwater intrusion, their salinity of groundwater has increased, and where there is a other way around, it opposite happens. Depending on that, we have put the color schematic diagram, and then try to understand the coastal groundwater characteristic, and we try to understand the seawater characteristic. So in that case, the groundwater, you can see that TDS, salinity, and like that, and we just match the difference or the similarity or dissimilarity and try to understand. So we have already pinpointed that where intrusion must be happening, and where there is a groundwater discharge happening. So then the low TDS and salinity will indicate of STD, and opposite will indicate seawater intrusion. I have much more interesting thing to tell about this pore water sampling. Whenever we suspect that there is a groundwater, then we take the pore water sampling. This is the pore water that we inject a little bit and then take the water from injection. And that water is and we do it in intertidal zone. So I told you that when there is a low tide, we go there and we take the sample and try to understand if now groundwater is going into the sea or not. So then this is the pore water sampling we are doing. We have already covered this much area, and still my members are in the field. Coming to the microplastic, this is emerging like the antibiotic, like David has presented. And microplastic is not only imported from the sand or this one, but many fish, of course, we can get inside their body. And it is not that only the plastic that we will use will be broken down into the microplastic. Even if we wash the clothes or that produces a lot of microplastic. So it is not so easy, because there is the different size of microplastic. Microplastic has been reported in the sediment of the sea sediment, but here we have reported in the river sediment and there. But from the perspective of the seawater, we have done so far, we have collected 64 samples and we have done the analysis. And Glujarat coast, there is a 2-3 method. One is visual sorting, another is chemical method, microscopic method to understand the microplastic. Here we have done the visual sorting, which is, now you can see that 1 kg we get 20 to 30 pieces of the microplastic and like that. So this is the little bit part of the microplastic. I hope I'm just showing the idea that we can have. Now, what is future perspective? Now, this is the last portion of my segment of my presentation. So isotope, everybody understands. So then I'm just talking about that how radon is found in groundwater. So if there is a radon present in the seawater, it will only come through the groundwater discharge. So then you can see that this is the salinity. Everybody understands that which one is seawater? So here in this graph, you can see that this is the seawater, which has and this is the groundwater. So there is a clear difference of radon activity, and this activity will vary if we have the sampling, if there is a groundwater discharge. Then isotope also, you can see that this is the seawater. This one is seawater where there is no groundwater discharge, and in the medium there is a groundwater discharge, and this is the groundwater. So if we will do the isotope estimation, we will know exactly that where the seawater intrusion is happening, the submarine groundwater discharge is happening. And this is the radon, and I told you that how much seepage, it means how much ml per meter square per minute of groundwater is discharging into the sea, that will reflect the amount of the radon. I have now the last one segment. So I am talking about is that from aquaculture perspective, not only these things are important, or microplastic or antibiotic resistant, metal is one of the also very key factor, because the metal will come to the in the coastal water and it will be very aquaculture, and so this metal accumulation in the aquaculture will be there. And this is in India and many developing countries, we don't have ambient water quality guideline for metals. We have the drinking water guidelines, but we don't have the ambient water guidelines. So from that perspective, it is very much important. And even if other countries that have the water metal guideline, they don't have the, it is based on total metal, not the metal speciation. And what is metal speciation? Metal speciation is that metal exists in the water in free form, it can be in the particulate form, it can be in the dissolved form, and even in the dissolved form, there will be organic and inorganic form. Now, we are thinking about aquaculture, right? So this is the biotic ligand, and if this fish is there, so it will interact with this metal differently. And if the metal is associated with the organic fraction, so then this will be digested or assimilated differently. So then the total metal is not enough, but the speciations are. And similarly, what kind of, like David has told that it comes from the canal or fecal contribution, so then the organic, the ligands will be different than the just industrial effluent. So then what kind of metal is coming with what kind of DOM, dissolved organic matter, is very much important, because that will affect the microorganisms, that will affect the, how it will biodegrade, and that will affect how much will be go to the sediment and how much will be available, and like that. So we have this kind of the reports in our, of course we have done some superbug, that is multi-drug resistance, and like that. And I have not concluded my presentation because still it is going on. But here, this is David giving a very this presentation, and then Meena and training he has been carrying out there. And so 2 times we also have a UKD project, and he visited there. This is the beautiful campus. Please visit us, or I will organize something. Thank you very much.
Thank you for your kind presentation. Okay, so now we still have the time for about 10 minutes. Maybe we can have 1 or 2 questions for the both speakers. Any questions?
So please ask question, otherwise it means you didn't understand anything.
Thank you very much both of you for the presentation. It's very interesting. My name is Kalaya. I'm working for NASA, and I'm working mainly with shrimp disease. I think the project of microbiome is very interesting, and we are trying to use the technique of the minion to look for many, to solve the problem of shrimp disease. So what I want to ask maybe for the Professor David, what are you going, I'm going to continue the project after this Newton IL, and I think it should, but I don't know the mechanism. I'm going to apply for more funds.
Yes, of course, but more importantly, you've got a partner here at KMUTT now who you can work with, who has the skills to do this. So you don't need to work with me. So now, with the team here at KMUTT, any future research project, they will be able to use that technology. So yesterday, one of the farmers came to the workshop we had, gave us some shrimp that she thought had white spot disease. So we will analyze those with our sequencing technology, and we can share the results with you. So I mean, I talked about resistance, but of course, disease is also important, and you can use the same technology to look at this, and we are doing it. And yeah, we are very interested in collaborating further and continue this line of research. But my key message is, now you have someone here in Thailand who can work with you. So you no longer need to do it with people in Europe.
I still think that collaboration, discussion is still necessary for the research. Okay, thank you for the first question. I have the second one. Sorry, this I was hearing a lot about this AMR, and you were told me that you have many antibiotic resistant bacteria in the water in Thailand. So my question is, normally, if there is some contamination like that, what is the solution for that? If you know that this environment have contaminated with a lot of antibiotic resistant bacteria, what is the solution for that?
So I think we very clearly show what the source is. Yeah? The source is our waste. Yeah? So the solution is controlling the source. So in Bangkok, you treat 50% of your wastewater. And 50% is untreated. You just discharge into the canal. And that's where the resistance comes from. So you need to expand wastewater treatment to 100% of the population. And that will solve a lot of these problems. Of course, you also need to reduce usage in aquaculture. But from the farmers we work with, they already tell us we don't use it. So that's been solved in some extent. You need to treat your wastewater. And to treat your wastewater, you need to pay for it, all of us. We need to pay for it. You cannot expect the government to do everything based on some source. So we need to be willing, we need to accept that we have to pay for the treatment of wastewater. Just like we have to pay for drinking water. We have to pay for electricity. Every time you cross a bridge, cross the river here, you pay a toll. So you're willing to pay for infrastructure. You also need to be willing to pay for wastewater. That's the solution.
And I would like to add, even if it is not directly addressed to me, that the antibiotic resistant problem, we cannot stop it. We can slow down it. Because there is no cure that we cannot say, hey bacteria, you cannot develop the resistance for this antibiotic. So one is that source control that David has talked, but antibiotic use is also very much important. That we should be saying that no, I will have some flu for 2-3 days rather than use the antibiotic every now and then. So the use of the antibiotic has to be restricted. Then there is the awareness that okay, the washing hand or those things is also very much in addition to what David has rightly pointed out.
I'm sorry for biotic. I think you already collect samples and the sequence data should be very, very useful for further analysis. So we hope to have a collaboration, and as we are working with the aquaculture, and we also study the microbiome in aquaculture pond too. But one thing I saw in your slide, you show the relationship between the AMR genes and with the abundance of 95 bacteria, as one graph shows. What does it mean?
Okay, I mean this is just an example because with sequencing, so we looked at fecal bacteria, we can see those, and I show there's a strong correlation with resistance. So that tells me the resistant bacteria are fecal bacteria. So you take antibiotics, your bacteria and the gut are resistant, they get into the environment. Now with sequencing, we can also look at other bacteria. For instance, Vibrio cholerae. There's no correlation Vibrio cholerae antibiotic resistance. What I showed is there's no correlation nitrifying bacteria antibiotic resistance. There should be a correlation nitrifying bacteria, nitrogen, for example. Yeah, it's just an example. But with sequencing, we can look at fecal bacteria, nitrifying bacteria, Vibrio cholerae, all of bacilli, probiotics, we see everything. That's the power of this technology.
Okay, maybe open it.
bit about the future collaboration if you are interested in both at KVDC and NASA and with our colleagues here. KVDC has a scheme called Visiting Professor Fund, and we can invite a professor from abroad or to come here for discussion to set up a workshop or teaching class for 2 weeks here. You can all use this scheme for maybe future collaboration and talk about proposal and so on.
Okay, maybe the last question.
So thank you, Manish, for a very interesting presentation. So I have one question related to the result. In the result, you said that for resistant antibiotics resistant in canal and in the pond, right? In our pond. And I have 2 questions. First, did you measure any concentration of antibiotic in the canal and in the pond? The second question is, do you think that any impact of disinfection in the pond? Like farmer frequently use the disinfection chemical in the pond. So do you think that it can impact us? There's no resistance in the pond. Thank you.
I mean, it's very clear if the farmer would be using or if the farmer is using antibiotics, they will produce resistance. But in these ponds, the farmer told us we are not using antibiotics. Yeah? We did the measurements in the previous study, and this confirmed, no, the levels is very low. That's why we don't see it in the pond. Now we take antibiotics, so in our gut, the concentration is very high, 1,000 times higher than in the water. So that's why our bacteria are resistant. We release the bacteria into the waste, it gets into the environment, that's where the resistance in the canal comes from. But let's be clear, if the farmer uses antibiotics, then they will be part of the problem. But our farmers are not using antibiotics, and therefore they are not contributing to the resistance. With chlorine, we haven't looked at this yet. But I think the problem is you use chlorine to disinfect, you kill all of the bacteria. Now 99% of all bacteria are harmless or beneficial. So you kill the bad guys, but you also kill all of us at the same time. So that's like the sledgehammer approach to a problem. So to kill the criminal, you kill everyone. So I think that's also not the best way. The best way is to try and understand what's going on in your pond. You can do it with the technologies that we've now demonstrated. And this should help you understand what's going on and have targeted interventions. And we'll hear more about some options for treating the water in the afternoon.
Thank you very much for
So I have one question to him, because no question to me. Just to have the benefits of this discussion, of course I can ask him privately, but it will not help others. So here this is a multi-drug resistance, and this is the sulfonamide, and this is the tetracycline. Tetracycline is first generation antibiotic, right? So then what is the difference have you observed in the new age or 4th generation the antibiotic resistance, or even the 1st generation? So is there any difference between the generation to generation antibiotic resistance?
Yeah, I mean, I haven't looked, you've got such a wealth of data. I spent 3 days to try and present it, prepare for presentation, but there's so much more we can look into. I mean, the one thing you can see here on the slide, this type of resistance is just in response to stress. So it's like the bacteria is stressed, it gets everything out of the cell. So that's not in response to exposure to a certain antibiotic. And therefore there's no trend here. So that's just in the environment, all bacteria have this kind of resistance. I think tetracycline resistance, the level is relatively low. This may be because there's less usage now. So this is maybe even a legacy from previous usage. And then I would expect that the clearest trends are for the latest generation.
So some of the Indian findings which I have not shown in today's presentation, we have found is that in developed countries, the first generation antibiotics resistance is more. But in developing countries, the new generation antibiotic resistance is more. That is
because we still use first generation. So in the UK, they will try and use the first generation, because if you get resistance, you still have the second generation. So if you already go to the newest generation, you get resistance, then you don't have anything left. So that's because of how we use antibiotics.
Thank you to Dr. David and Dr. Manish.